Hey, welcome to Conversations with my dear friend, Jeff Conway. My name is Susan. This is A Different Kind of Walk. Hey friends, today we are thrilled because we get to speak with Bill Jones, who is a professor of physics at Princeton University. Bill earned his Ph.D. at the California Institute of Technology, Caltech, and was a scientist at NASA's Jet Propulsion Laboratory in Pasadena before coming to work at Princeton in 2008. The focus of his research is cosmology, meaning that he attempts to understand the contents and evolution of the universe. Enjoy the episode.
Oh,
Hello, Bill. Sorry if you've been waiting.
oh, no worries. Yeah, I'm actually still making my way across campus.
Perfect.
Yeah,
Perfect.
no worries.
I don't know if you actually know very much about this podcast that we do.
No,
Um,
not much. Yeah.
yeah, okay. So Jeff is in his 60s. Jeff was my boss at a previous job, and he had to retire early because he has, oh, wait, there he is, right there. He can tell you himself. He has a neuromuscular disorder.
Yeah.
It's degenerative. Hi,
Gotcha.
Jeff.
Oh, good morning.
Hey, what did I do this time?
Oh, nothing. I was just starting to introduce you and kind of why we do this in the first place. But if you want to say some of that yourself, go for it.
Okay. Um, well, I'm a friend of Susan's, Bill, and she takes care of everything technical for me because I'm
All
clueless.
right.
Um, so I was a pastor for 35 years and I
Okay.
got a strange neuromuscular disease that affects my walking and talking and movements. And I see things sometimes too. So,
Wow.
but I know that they're not real. So that's good and fun. Um,
And so we do this podcast about joy and pain going together, and we interview cool people like you who bring us joy.
so I'm excited to hear about you today. So that's a beautiful campus that you're walking across.
Well, half of it is gorgeous. The half that we're on has been a construction pit for the last 3 years. So
Oh
someday.
gosh. Yeah, that's too bad. Princeton's like the perfect college town,
Oh,
I
it is.
think.
Yeah, it's a nice place.
Yeah, but sorry about the construction.
Okay. I think I am up now. Is that
Yay.
working?
Yes, we can see you.
Okay.
So if you don't mind, tell us a little bit about yourself. I didn't put this on there initially, but like, where did you grow up? What made you want to go into science in the first place and study the universe?
Do you have brothers and sisters? Are you nice to them? Um,
Yeah, so my dad actually grew up on a farm in southern Illinois,
oh
and
wow.
he and his brother and sister all made it out to college, and my dad ended up going into sort of agribusiness there in Illinois and in Indiana, and my uncle stayed on the farm. And so my dad was working for a variety of companies, including like Orville Redenbacher out in Indiana. That's where my brother was born in Cincinnati, and then we lived out in Valparaiso, Indiana for a number of years. I was actually born in California, but then moved back out to Indiana when my dad got transferred back and forth. But by the time I was going through elementary and high school, middle school, we were out in California at that time. He was working for actually out at Hunt's, like Hunt's Ketchup
Mm,
Ah,
up there in Anaheim. So
okay.
that's how we ended up.
okay. Oh, good. And were you nice to your brother?
I would say I was nice to him, and he was really nice to me. You'd have to ask him though what his opinion was.
Is it just the two of you?
Yep, two of us.
All
He's
right. Yep.
Yep.
I
And
grew up with one brother. I had two sons, and now we have a granddaughter, and I don't know what to do with her. So, did you go to school for undergrad in California also?
So I went through the public school system in California up through high school, and then was actually an undergraduate here at Princeton.
Oh,
Okay.
okay.
Yeah. And I was always very interested in the sciences, not so much in math, but I would say that, in going into college or approaching college, it was one of my interests, but by no means the only one. I sort of went into college thinking I might be a Spanish lit major, and by the time I got to college, it became very evident that I didn't have any talent for that. Um, and
Mhm.
then after Princeton, I went back to California for graduate school.
Okay. All right. So just tell me a little more Spanish lit. So did you just start taking all kinds of classes at Princeton and kind of started focusing on the physics?
Yeah, that's pretty much it. Well, Princeton, along with many other schools, has a language requirement, so you have to take some language there. But I had taken all the Spanish that I could in my high school, and growing up in the Los Angeles area, more than half the people speak Spanish. So
Right.
I definitely thought I spoke better than I did, mainly because I was speaking to the folks on my soccer team and in the community, and that wasn't necessarily the same kind of Spanish that was in the Spanish lit class.
Yeah.
Um,
Yeah.
so it
No.
so that was an eye opener.
No.
And yeah, but it was pretty evident after my first year there that wasn't my talent.
Okay. So a draw towards physics. What about becoming a professor? Was that why you wanted to go on to more education, or were you looking at going into a field where you could use physics?
Well, it was really the research side of things that I really enjoyed. So, there's many subfields of physics, and the one that I've sort of been plugged into since, going all the way back to college was sort of on the experimental side of astrophysics. So my interest in cosmology kind of focused to the area of instrumentation into millimeter and microwave instrumentation for very specific science investigations. That was great fun doing optics and detector design. And I would say that I enjoyed doing that. And so I just kept doing it more so than having a real, very carefully laid career path and plan for life. But that brought me into graduate school where I did more of the same and just kind of developed from there.
Okay. So let me ask you a real serious question. Do the characters on The Big Bang Theory really match the kind of people that you were working with?
So I get asked that all the time.
I bet you do.
And to be perfectly honest, I've never watched an episode.
Very good.
And you can probably kind of imagine why.
Yes, very
I will
good.
say though that so my wife and I, when I was in graduate school, my wife and I were sort of dorm parents in one of the undergraduate residences there at Caltech. And from everything I can piece together, yeah, it's pretty accurate.
So did you meet her in at Princeton or did you meet her in between or when did you guys
Well,
get
we
together?
first met in the airport in Guatemala City.
Wow.
I knew that she went to Guatemala, that she was in the Peace Corps
Yeah.
and whatever, but why were you there?
Well, I had in college and in the first part of my graduate school, from Los Angeles, I would travel there all the time. So anytime I would get a break, I'd head to either Mexico or Central America.
Hmm.
A, because it's a beautiful place, lovely people, and just an amazing place to travel. But B, because it's really affordable. And as
Hmm.
a graduate student, I could almost live cheaper being there than in Los Angeles.
Oh,
Um,
interesting.
so I'd actually traveled around a bunch there, and I also had a connection to Molly through her extended family. So growing up, her cousin was one of our neighbors. And we would be at their house or they would be at our house for Thanksgiving all the time. So I knew her cousins and her extended family very well. Had never met her though. And then, yeah, it just came to be that through actually one of those cousins' wedding, it was evident she had come up and we had kind of heard about her that she was down in Guatemala in the Peace Corps. So the next time, I was thinking about a trip down there, we started corresponding and the rest is kind of history.
Oh, wow. Very
And by
romantic.
corresponding at that time and in Guatemala, that means by letters.
Yeah,
Right.
There was no email.
Yeah. Yeah.
that's so
Wow.
sweet. I
That's
love it.
pretty neat.
So,
Oh,
speaking of Molly, I've worked with Molly for the past 2 years, and one day we were talking about places that we would like to travel to because I know she's a world traveler. And I told her that my dream was to visit Antarctica because there's this
Ah,
tiny Russian Orthodox church there,
yeah.
which is fascinating to me. Wait, now that you said yeah, now I'm like, have you been there? Anyway,
Well, I haven't been to that church, but I know of it.
okay. Wow. Okay. So
Yeah,
anyway,
yeah. Yeah.
I really want to visit. And I told her this, but I was assuming that this was going to be like something crazy that I said, no one goes to Antarctica, right? And then she immediately told me that you have gone there several times and you build essentially like gigantic hot air balloons that are bigger than football stadiums, which you launch into outer space in order to study the Big Bang.
Well, they're helium, not hot air, but yes.
Okay, well, there
Oh,
you go. And my jaw just dropped. I was just like completely blown away. So thank you for correcting me on the helium. Otherwise, is that somewhat accurate? Like,
Yeah, pretty
what do
much. So I've been a number of times for several different projects. Some of them, people think of Antarctica and they think of the South Pole as sort of one and the same. And one thing people have to remember is that Antarctica is an enormous landmass. If you plopped it down on top of the continental US, it would smother it.
Mm,
So there are many different places in Antarctica. The Russian Orthodox Church is not in a location where I go. I've gone in the past to the geographic South Pole for an experiment there. Several times I've gone to a base called McMurdo Station, which is sort of the main logistical hub for almost all activities down on the continent. And about 10 kilometers away from McMurdo, there's a seasonal station where NASA has a seasonal facility where scientific ballooning's done. And they've been doing that for, gosh, since throughout the 90s.
is there a reason it has to be at the North or the South Pole?
Sort of. With these balloons, what one likes to do is to launch them and then leave them up as long as you can. There's two things that would prevent you from doing that. One would be complications with flying over populated areas,
Mm.
mm,
and the other one would be a day-night cycle. The temperature variation that would come from a day-night cycle would cause the type of balloon that they fly to come down. It wouldn't stay up.
mm,
At the time of year when these balloons are launched, the sun never sets down there, so the sun's always up.
Uh,
And so that allows the balloon to stay flying. It also provides you with continuous power for your experiment.
mm.
And also there's no one down there, so you're never going to fly over a populated area. And then the final reason that balloons are launched from there is that around Christmas every year, there's a wind pattern in the stratosphere that sets up, which historically has been very regular, although it's getting less so in the last decade, in a circular pattern around the South Pole. And so what happens is you launch a balloon and it basically goes around in a circle around the South Pole. It
uh,
comes back. In some cases, it will fly right back over the area where you launch it. Not so much anymore, but that has happened. So that, of course, makes it convenient from the point of view of recovering your payload.
Yeah.
Because remember, Antarctica is enormous, and if you land something on the opposite side of the continent and there's no infrastructure, it's a massive challenge to go out and get it.
to get over there. Yeah.
Yeah. So like, how long do they stay up?
Typical is about 2 weeks, but that there's a long tail in that distribution that goes to over 40 days.
Okay.
Oh, wow.
So
You-
what is one of the most interesting things that you've learned from these sorts of experiments? And really just like what questions are you even asking in the first place when you do them?
Yeah, so first of all, from Antarctica, there's a wide range of different science that happens there. The sort of science that I do is just a part of it. So anything from, certainly earth sciences, but also even within astrophysics and physics generally, there's a wide range. The study of cosmic rays is a sort of unique niche for that platform. What we do with it is we have been making observations of the cosmic microwave background. So this is the thermal radiation that's left over from the very early universe.
Mhm.
Um, and you can, I think a nice way of thinking about what it is sort of taking a snapshot of the universe when it was a much more simple thing than it is today. So think
Mhm.
of something just a few minutes after conception. It's a much more simple organism than a 50-year-old person is. And so by studying the universe at that early age, you can kind of strip away all the complications that comes from emotional damage and work accidents before any of that complicated stuff happens, you just have this nascent object that you can study the properties of it and make fairly direct relationships between it and some theory that you might have about how it's going to develop. It's a much more simple thing to compare than the present day universe is, that has complicated things like chemistry and stars and all of the phenomena that we see around us that are very complex didn't exist back then. And so it's a very clean slate, if you will, for studying.
So is this before or after the Big Bang that you're talking about? Or I
Yeah.
don't even know if you would call it that, but teach us.
So the term Big Bang, I think, is a terrible misnomer. And it gives the public the wrong impression about just about everything. The main thing it gives the public the wrong impression about is that something went bang
Mm.
at some place or point in time and space, right? That something went bang. And that's just not the case.
Right. I guess the way I understand it, it was this thing, and then it just kind of blew up and went all different directions and created. That's my very basic.
Well,
So
the right way to think
obviously
about
that's
it,
wrong.
it's not wrong. It's just not strictly correct. The right way to think about it, instead of starting from then and working to now, is to go the other direction. So start from what's now, and then we'll work our way back,
Uh,
because that's all on very firm observational footing, and we don't have to speculate. So it is the case right now that when you observe very distant objects, so things like galaxies that are so far away from us, we're not gravitationally connected to them in any way. It's the case that when we do that, no matter in what direction we look, those objects are moving away from us,
Mm.
right? And moving away from us in a very consistent way, in the sense that there's a fairly tight distribution between how far away they are and the speed with which they're receding from us.
Mm.
So you can scratch your head for a minute and convince yourself that that's kind of consistent with what would happen, for example, if you were to make raisin bread, and as that loaf expands, you can imagine measuring the distance. If you were to take one raisin and measure the distance from that raisin to the surrounding raisins, the
Mm.
same thing would happen. Like all the raisins are moving away from the other raisins, right?
Mm.
okay.
Not that there's any one raisin that's the center of all that expansion. There's nothing special about any one raisin. Everything is expanding around it. And
Okay.
that seems to be what's happening in the universe.
Mm.
So the implication of that is that if you were to turn time backwards, so go back in time rather than looking forward, the implication is that things would have been closer together. Everything would have been more dense at some earlier time.
Mm.
And you can turn that clock back as far as you like. And you can imagine that, as we go back in time, the universe is getting more and more dense, just like a diesel engine. As that gas gets more dense, it's also going to get more hot.
Mm.
So along with that density increasing as we go back in time, the temperature is increasing as we go back in time. And you can turn that kind of arbitrarily far back until that temperature gets so hot that everything in the universe, which to a very good approximation is just hydrogen gas, ionizes, just like a candle flame,
Mm.
right? It's so hot that the electrons are pulled away from the proton. And so there's a point in time that if you turn that clock back far enough, everything in the universe, no one place, but everything in the universe was very hot, so hot that it was a plasma. You can call that the Big Bang if you want. It's a really hot kind of fireball thing. It didn't happen anywhere, it happened everywhere. It's
Mm.
just a state of the universe. And you can continue to turn that clock back, and yeah, it's hot as a plasma, but it could be even hotter. And as you turn that clock back, it does get hotter. And you can continue doing that thought experiment all the way back to where it's so hot, it's like a nuclear reaction, right?
Mm.
And we understand all of the physics from everything we've just described. We can replicate that in laboratory environments. And so we understand how things work. And you can come up, therefore, for predictions for what should have happened at each stage of the universe like that. And you can play that game all the way back until you get to nuclear reactions, and even hotter than that correspond to like the conditions that are inside the atom smashers, like the Large Hadron Collider. And again, the whole universe was that way. It wasn't one spot. Nothing went bang. It's just that everything's hot. And essentially, cosmology is the practice of turning the clock backwards as far as we can and making the relationship between what the conditions in the universe would have been and the physics that we understand from laboratory experiments, essentially, and understanding the way in which the universe evolved to the place where it is, and therefore, what it had been at some earlier stage. When we talk about the cosmic microwave background, what we're talking about is the light that is propagating throughout the universe from that stage where those hydrogen atoms just became ionized. So not the earliest stage, not the nuclear reaction stage. You could also call that the Big Bang if you want. It was really hot. But what the cosmic microwave background is the light that remains from that stage when it went from a plasma to a neutral gas. And it actually made that transition, relatively speaking, quickly. And so once it transitioned from a plasma to a neutral gas, the thermal radiation that was present in that hot era of the universe was free to just travel throughout the universe and hasn't interacted with anything since. And we can collect that light and study it.
That's
So
fascinating.
that's what we do from the reason that we go to Antarctica to put our instruments on balloons is that the wavelengths that correspond to that light right now are ones that are highly attenuated by our atmosphere. And so one way or another, we need to get up above the atmosphere in order to make clean measurements of them.
Do you have specific questions that you're trying to answer when you're doing them, or are you mostly just measuring them, trying to collect data?
Both, but we do have specific questions. So, the scenario that I just described, I would say was fairly well understood, going back to the late 80s and 90s. But the technology was running behind that theory. So there were all these amazingly exciting ideas about what one could go out and measure, but the technology wasn't there to do it. Since the 90s, the field has progressed, technologically speaking, just phenomenally. And it progressed from the point in the 90s where we could first make statistical statements about the fact, yeah, we can measure this radiation. It's sort of a proof of principle that we could measure this signal, to the point now where we make extremely high signal to noise images of it. It's not routine, it's not easy, but we have instrumentation that's sufficiently sensitive now that we can really characterize these signals with a very high signal to noise. So I guess to answer your question, initially just showing that story that I was just describing actually fits with the data initially back in the 90s was a big deal, right? Because, while it was a great idea, there wasn't any observational proof of it per se. And so just confirming that paradigm that we described is more or less correct was a really big deal in terms of our understanding of the evolution of the universe. Since then, we've been able to do more. Rather than just saying, yeah, it's basically the right picture, the theorists can go out and they can calculate very specific statistical predictions for what the characteristics of this radiation should be. And those predictions depend on things that are very fundamental. So what is the universe made of? What are neutrinos like particle physics even? And their predictions for what we should observe depend on all these parameters about physical quantities like neutrino mass and the amount of baryonic matter, the existence of dark matter and dark energy. And then we can go out and measure these signals and compare them to those predictions and see which of those predictions are false, right? And sort of winnow down the huge range of things that could be true to the more narrow range of things that might be true.
Can you give me because I know I will need to go back and do this myself if I don't just ask you. Can you give me a really quick definition of what dark matter is?
Nobody knows. Literally, it began being called dark matter because it doesn't produce any light. But the best we can tell you is that it's matter. So think of knock on your desk. It's not that. So it's nothing physical that have any familiarity with. It's some particle, we think, although we don't know that, but it's some stuff that interacts gravitationally. But unlike your table, it doesn't interact through like electromagnetic forces or through the nuclear forces. Strong, apparently it doesn't interact at least much through even the nuclear weak force, which is really weird. And it's not something that fits nicely within the particle physics models that theorists have. But we observe it indirectly in many, many different ways. And all of those different ways point to the same conclusion, that it's some sort of like a particle that only interacts through gravity.
If you may, speak to me like I'm a first grader who loves raisin bread.
Yeah.
From the plasma to the neutral gas, is there a line that you can describe to where do galaxies come in? Where do
Yeah,
planets come from?
absolutely.
Where does our planet come from?
Yeah, so there is, and it's a very active field of study to understand just how it is that the distribution of objects like galaxies and clusters of galaxies, and then on the smaller scales, like our own solar system, how those form. And we can trace those all the way back to those images I was telling you about of the cosmic microwave background radiation. It turns out that when you observe the cosmic microwave background radiation, so that thermal radiation from the very early universe, it's remarkably smooth. It doesn't matter which direction you look. The radiation from the left is to a part in 100,000. It's the same temperature. It's the same intensity as the radiation from the right.
Mm.
And that's very unsettling.
Hmm.
And the reason that it's unsettling is that the light that came to me from the left has never had a chance to talk to the light that's coming to me from the right.
Uh,
How could they possibly have agreed on a temperature? How could they
Mhm.
possibly agreed to be the same intensity?
Mhm.
How would it know? Like they've never been in causal contact.
Mhm.
That remains at the forefront of our attempt to understand early universe physics. It's a fundamental, it's an observational truth, which is the implications of it are really kind of profound.
Hmm.
Now, when you look in more detail, they're not exactly the same intensity. There are fluctuations from point to point on the sky. It's not the same intensity everywhere you look. And those fluctuations we can actually understand as the seeds that formed the structure that eventually turn into galaxies, clusters of galaxies, and therefore eventually into things like stars and our own planet.
Well, I know that you happen to be a churchgoer.
Yeah.
And depending on people's backgrounds, sometimes religious folks have a lot of issues with scientific folks. So I'm wondering how you end up holding both of those worlds together in your own person.
All just a terrible miscommunication on both ends.
Yeah, well, talk about that.
Yeah, no, so you're right. I grew up as sort of a mainline Presbyterian. We still go to the Presbyterian church here in town.
Hmm.
And I'm always astounded that this is even a topic of controversy. And ultimately, what it does, it boils down to the question of, are there limits to scientific inquiry? Are there questions, sensible questions a person can ask that can't be addressed scientifically? And before anybody starts a science versus religion question, I think they really need to address that question first. And if you can come to an agreement on the answer to that question, then I think it's sort of the discussion's kind of over. And if you can't, well, then you need to continue talking and understand why there are limits to scientific inquiry. Science can answer a lot of things, but it can't answer everything.
In our correspondence, when we were setting this up, you mentioned that scientists don't necessarily like to admit that.
Oh, they hate it. I hate it, honestly. Like it'd be great if there was some theory that I could come up with and an observation I could make to test it that would push our understanding earlier and earlier in the universe. That's literally what we do every day. We're trying to push that back as far as we can. So, yeah, if I can think of a way to do it, I would do it. Do I think I'd be successful ultimately? No, because for very fundamental reasons, you can show that no matter how well you do, there's always going to be a well-posed question that can't be addressed with science.
the next step.
There's
Next
always going to
step.
be a next step.
Yeah.
Yeah. And I think that is honestly fairly intuitive, right? Because remember how we were talking about how the universe was, if you turn time backwards, it was getting more and more dense and hotter. You can always ask the question, well, what happened before that stage? Or what happened before the stage where, the gas became ionized? Well, it got even hotter, and then you had like nuclear reactions happening. Okay, fine. What happened before that? Well, it was hotter than that.
Hmm.
And at some point, you can always ask what happened at some earlier stage. Now, it's not restricted to cosmology. You can ask all kinds of questions like that, very well posed questions that in principle can't be addressed. So what do I mean by that? I guess applied to cosmology, you can turn that clock back to energy scales or temperatures if you want that are much higher than anything we can make in a lab. Like no matter how many billions of dollars we invest in particle accelerators, we'll never approach the energies that correspond to those in the early universe. We just can't. You could build a particle accelerator the size of our solar system and it wouldn't come close, just off by orders of magnitude. So I can't tell you how physics works at those energy scales because I can't set it up on a bench top and test it, right? You can tell me a theory about how you think it works, but if I can't test it, then I don't know. And that's always the case. And so what we're doing essentially, one of the reasons that cosmology for me has been so exciting is that the universe offers us an opportunity to get beyond what we can measure on sort of human scales, right? The universe has given us neutron stars. The universe has given us the Big Bang, the cosmic microwave background radiation. And if we can observe those phenomena are happening at energy scales that are just mind-blowingly beyond anything that we can make in our solar system. And it offers us the opportunity to test those laws of physics. So the universe is kind of the ultimate laboratory.
Yeah.
Another question. So I don't know. I can't think of a person that I know that would say the universe was created in 6 24-hour periods, 6 days, resting on the seventh. The literal part of that.
They're out
That
there.
seems
Oh, yes, for sure. I know a lot of folks.
they are, and that's the only place that the challenge of
Absolutely. Yeah.
faith and science hits off each other. And I don't
And the same criticism can be directed at the scientific community. They're absolutists on both end. And in fact, I think that there's probably that absolutists are sort of more common on the science end than on the other.
I look at chapter 1 and chapter 2 of Genesis in this amazingly poetic way. Um, Everything out there was tohu in Hebrew, formless and void, ruach, the spirit of God resting over that. Just and the creation, the way it's described is just a beautiful gift, but it's not a science book.
Does ancient Hebrew have a word for plasma?
Yes. Um, Blob.
It's fair.
Yeah, it's just so beautiful and poetic, and I don't think in any way they need to bounce off each other. And all of Scripture, there's nothing about it that's a science book. It is the story of God's redemption of humanity to me. So you do not have to fit every point that you're speaking about today into that 6 days, or how does that fit and all those kind of things. It's fascinating the way scripture develops in those first two chapters, but listening to you and looking at you, we get to see you. People that will hear this won't get to see you, but the enthusiasm on your face as you're talking about this, I just imagine I could be your student, but it's just fascinating to have somebody so enthusiastic about what they're teaching.
No, no, I'm biased, but cosmology and our ability even to wrap our heads around the scales that we have so far, it just is amazing to me that we're able to do that. It's just a joy to be able to sort of on a daily basis get to spend the time to not just think about these things, but also try to go out and measure them.
Right. So you brought up a word here, cosmology, and isn't that the study of putting makeup on people's faces? I don't quite
I get
understand.
that a lot. Yeah, I know a cosmetologist also.
Oh gosh, I'm sorry. I'm being the old man dad character using all the same jokes you've heard
No, I've been
30
introduced to a
years.
pharmacologist before, so it's fine.
Well, Jeff, I agree with you in terms of like I feel like when I watch you talk about this stuff, Bill, there's definitely a sense of like I can encounter like the joy of God in you, if that makes sense. Whereas I feel like some people would think like the more I delve into science, my faith has to get smaller or I have to put it into a box. I feel like just talking to you makes it feel like God is that much bigger.
Yeah.
Yeah, I mean, science puts things in boxes for sure, which is no problem for religion as long as you are interpreting things rather than taking them verbatim. It's
Mm,
the practice of science definitely it prevents me from being dogmatic in any way, right?
Mhm.
The only thing that I do know is that we don't know everything.
mm,
And we
Mhm.
can't know everything.
right.
And that opens the door for faith.
Mhm.
Amen.
Yeah,
Yes.
so do you feel like if science has limits in answers, and maybe we don't need to be searching for the answer to everything in general, but like if science leaves space to find answers elsewhere, is religion actually a place where we can find answers, or do we overplay that as well?
We got to be careful about what you mean by answering a question.
Mm,
We're very careful about what we mean by that in science. I guess when I think about whether, if you ask me if I can answer a question, I think of that as a scientific question. Like, can I disprove a hypothesis or not? If the answer is yes, you can disprove it, then yes, then I can give you a definitive answer. If the answer is no, you can't, well, to me, then we're talking about philosophy and or religion. And what does it mean to have an answer there? I don't know. I'm no philosopher, so I don't know what it means to have an answer if it can't be demonstrated.
Well,
mm,
I would take that as the journey of spiritual formation, that as we continue to understand God working in the world, God working in our lives, it's not that there's a specific answer for everything. To me, there's a black and white with God. Yes, God is present, God is here. After that, that spiritual formation deepens our relationship with God, and God is relationship, and that is not a black and white question either. I don't think how people experience faith and that relationship in different ways, and
mm,
that's okay because we all are given gifts in different ways, and that's how we can experience God
yeah.
also.
My husband loves to quote the Simpson episode where the daughter Lisa accidentally creates life. And then from the life, they're all asking, all the little tiny people are asking Lisa as though she's God. They're asking, like, well, why did bad things happen to good people? And then this one random guy shows up and is just like, why am I so fat? And my husband thinks it's just hilarious. But like, um, yeah, those are the sorts of questions where it's like, I don't know if we will ever actually have answers to like why do bad things happen to good people? Because you're right, like you can't actually test that. You can't measure it. It's not a scientific question. And then it does leave a lot of space for us to go into philosophy and theology and our understanding of who God is and how present God is in all of our suffering.
Well, Bill has never seen The Big Bang Theory on television. I have never seen one episode of The Simpsons.
I've seen the symptoms.
Oh gosh, well, do have a good day and always remember you are a dearly loved child of God.
Well,
So
thank you. That's much
go with
appreciated.
that.
Sounds good.
All
It was good
right.
to meet you guys.
Thank
Yeah,
you
thanks,
very much.
Bill.
Yep. See ya.
Thanks for joining us for A Different Kind of Walk. Until next time, live well.